Very good. So yesterday we had talked about how to go from a particle physics predicted spectrum of stable standard model particles per annihilation to the actual signals that we see at our detector, taking into account the propagation of charged particles through our galaxy and the sort of line of sight integral of particles that travel on straight lines to us through our galaxy. A student asked me a good question actually after yesterday's lecture, which is like, is this it? What about, does this capture all the effects that we might need to worry about? And the answer to that is no. These are effects that you want to think about, but you can of course go beyond that. Are we good? Okay. Yeah. So I want to begin today by just giving a few comments on that, then wrapping up a couple of other just points that I wanted to make about the J-factor calculations. Then I want to briefly outline some of the key backgrounds and uncertainties that you're going to see when we look at real searches. And then I'm going to switch over to slides and we'll go through the kinds of invariant searches that experiments have actually done. This will not be a complete set, but I'll try to highlight the ones that give the current strongest constraints and that illustrate the concepts that we've been talking about. So let me first just say a little bit about what there is in terms of what particle propagation beyond what we've already discussed. So one thing that can happen, so we talked about taking into account redshift for photons and neutrinos coming to us from far away in the universe. You can also have effects where some of those particles don't make it to us, where there's some absorption along the way. And this can be accounted for just by like adding like an e to the minus optical depth term inside the integral that we talked about yesterday. So, yeah. Let's try a couple of things here. But more generally, you can have a situation, as we discussed a little bit in the case of cosmic rays, where the particles are not just disappearing when they get absorbed, they are producing some cascade of secondary particles. In that case, what you typically will need to do is write down equations that describe the propagation of the primary and the propagation of the secondaries and solve those equations simultaneously. If that's within our galaxy, then you may be doing this in the context of all the particles produced to diffusing under the galactic magnetic fields. More generally, you may need to do a somewhat customized analysis for this kind of case. Examples are if you have very high energy photons traveling through our universe, for sufficiently high energy photons, the universe becomes opaque because the pair production cross-section on the radiation background becomes large. So a sufficiently high energy photon traveling through the universe will hit a CMB photon or an IR photon or an UV photon, and it can pair produce. And then that electron and positron will propagate potentially, like as we discussed for charged particles yesterday. And for very high energy electrons and positrons, typically one of the major loss mechanisms is inverse Compton scattering, as we discussed yesterday. So then that produces more high energy photons. If they're high enough energy, those photons can pair produce again. And so then you get a cascade. And so the effect of that is to convert your sort of original high energy photon into a large number of photons that are too low energy to pair produce through this cascade. So that's one example. There's a question there.
Yeah. Why is that term a decaying exponential?
So this would be, so the absorption term, this would be like some measure of the optical depth. So it's just saying that at some redshift, there's some probability for the particle to get absorbed. If I compound that over many steps, then I'll get essentially an exponential decline. It's like a spin depth in a material. It just measures the opacity of the universe. Okay, so yeah, so more generally, and we'll see. So more generally, interactions produce secondary particles. And we'll see when we look at the constraints that these secondary particles can actually sometimes be more observable than the primary particles themselves. Like if you have something that produces a very high energy photon, like an EEV photon, you might say, well, we have telescopes that can look for very high energy photons, but actually the stronger constraints sometimes come from the EEV photon has cascaded and produced a very large number of 100 GeV to TeV photons. And our 100 GeV to TeV gamma ray telescopes can actually set better constraints than the EEV telescopes in some of these cases. So in that case, you need to track these particles and their propagation. So this tends to lead to, writing down some set of coupled differential equations for the propagation of the different species that are involved in the cascade. And I'll give you another example of that, which is also written up in the lecture notes, which is particle propagation in the very early universe. When you do the detailed calculation of those estimates we talked about on the first day, and you think about particles injected into the universe through dark matter annihilation or decay, how do they end up ionizing and heating the gas? Because it turns out that a 1 TeV electron or photon injected at redshift 1000 is actually a terrible photoionizer. Its ionization cross-section is extremely tiny. And if the only thing that it did was like prompt ionization or free streams through the universe, then not much would happen. We wouldn't get much of a signal. But what actually happens is that those high energy particles, when injected into the universe, undergo a whole bunch of cooling and scattering processes that end up converting their energy into a much larger number of low energy secondary particles, which can be efficient ionizers. So I'll go through an example of that and how it gives you the CMB constraints later. But in general, if you find yourself with this problem where there's a complicated cascade, sometimes there will be like analytic or semi-analytic expressions in the literature, but often you just have to build a custom numerical analysis. So yes, you can go beyond the J factors or cosmic ray propagation that we talked about earlier, but they tend to be, like understanding how photons and electrons and positons propagate tend to be pretty key ingredients of any of these cascade effects. Question?
How do you discriminate cascade of?
How do you discriminate that this is a cascade because you want to detect one particle in the final state?
So you will see the energy spectrum usually. So right, so the question, okay, good, we have a mic, I don't need to repeat the question. Very good. Yeah, so while like from one particular annihilation, indeed, they'll spread out all over the universe, you will typically only see one, you will most likely only see one particle from this cascade, because A is very small compared to 4 pi r squared. Like most annihilations that happen, you may not see any particles. There are going to be many annihilations or decays happening in any appreciable volume of dark matter. So you get to basically take, you will get many photons from many different annihilations or decays, and they will build up an energy spectrum for you. And so the energy distribution of the particles will vary depending on how many steps it's gone through. That said, being able to distinguish, say, did I have a 1 EEV particle that decayed and made a cascade and eventually gave me a bunch of 100 GeV to 1 TeV photons, distinguishing that from I had a multi-TeV particle that decayed to something, that decayed to some quarks, and then they hadronized and they made a lot of lower energy hadrons, and then they decayed through a cascade and made gamma rays. You would look at the energy spectrum, but in some cases it may be hard to distinguish those two because they'll both just sort of look like a continual bump of emission. So then it'll come down to how well you can measure the energy spectrum and how well you understand the backgrounds. But the discriminator would be the energy distribution. So it's, where at your telescope, if I plot E squared DME versus E, like maybe the true signal for the cascade is like this. There are a few of the primary particles that haven't scattered at the top, and then there's a continuum of lower energies. And maybe from your other competing dark matter annihilation model, maybe maybe the spectrum looks like this or something. And so then if you've got a good telescope and you've got a lot of photons, then you can tell the difference between these two, and you can do a fit, tell which model is the best. But like you're right that it may be hard to disentangle exactly what fits went into the cascades. All you can do is take your theoretical models, forward model what signals you would expect to see. And usually this is what you do. You take a range of theoretical models, you forward model what signals you expect to see in the data using the techniques that we've discussed, and then you just compare that to the data points that you have and ask which is the best fit. And you may well find that there are multiple models that you can't distinguish between. It's just uncertainty. Okay, So that was mostly what I wanted to say about you going beyond the basic calculations that we've done. Yes, sometimes you'll have to do it. I'll give you an example later, but what we've done are usually among the building blocks. Okay, so a couple of other remarks that I wanted to make about J factors before we move on to switches. So the J factors or D factors that we talked about last time are line of sight integrals of the dark matter density distribution or the dark matter density distribution squared. So in order to work them out and in order to work out our expected signal from any region of the sky, we need to know the dark matter density profile. So I mean, you've had these nice lectures from Annika on how to simulate those dark matter density profiles. Those are often the inputs to trying to estimate what the dark matter density distribution is. In some cases, we can also get observational inputs from looking at stars and the gravitational pull on stars by dark matter of the dark matter density. So if we look at what kind of density profiles we get in simulations, if we focus on first on simulations with dark matter only, and the baryons, one of those axes that Annika talked about yesterday, then it's usually true. The density profiles of halos are usually modeled by NFW, Navarro-Frank-White, or Ernesto density profiles. So these profiles are both generally rather steep towards the center of the galaxy. So we sometimes talk about a cusp. So the functional forms of those two profiles of the NFW, the density profile goes like this form. So basically a distance is much smaller than the scale radius. This is like a 1/r profile for the density, and distance is much larger than this characteristic scale radius RS. This is a 1/r cubed profile. And in between it goes to a sort of roughly 1/r squared scaling, and that corresponds to the flat part of the rotation curve. And that's right around the scale radius. Like the scale radius is where the slope is where the logarithmic slope is -2. So like for the Milky Way, roughly speaking, you can look up the literature and find what the most up-to-date value is for this number, but usually we take RS to be somewhere in the ballpark of 20 kiloparsecs. So then, so the Ernesto profile, which is a little bit more complicated, but a better fit in many simulations, is that both are, reasonable enough, simple descriptions of the data, but they're often used and tested against observations or simulations of the Milky Way. It's like this. So this has a scale. So this has a scale radius that's often called R-2. It corresponds to where the logarithmic slope is equal to -2. And so this is analogous to RS. For NFW, you can think of both of them as like scale radii. And this parameter alpha tells you tells you something about the scaling of rho with radius, tells you something about the steepness of the cusp. And again, for the Milky Way, the typical values that are taken for alpha, the Milky Way and similar halos is about 0.17. Now, as you heard from Annika yesterday, once there are baryons in the simulation, there can be complex and non-trivial interplays between the baryons and the dark matter. And as a consequence, in regions where there are a lot of baryons, such as the centers of halos, this dark matter density profile is pretty uncertain. So you should keep this in mind whenever you see a constraint from looking at the galactic center. Check which density profile we're using, and be aware that the answer may change by a couple of orders of magnitude, depending on what density profile you're taking. So this is just a general caution for galactic center searches. Because if we have one of these cuspy profiles, the galactic center is a great place to look at and to potentially find a signal. But you have to be aware that there's this large systematic uncertainty in signal prediction. So because we know that the baryons may be altering the distribution fairly significantly, people also often consider chord profiles where the density flattens out within some radius towards the galactic center. Or And these chord profiles can be sometimes built by just like taking an NFW or an ASTO profile and then setting the density to a constant within some radius. Like that's one way to do it. But another way, another prescription, another parameterization that's often fairly commonly used is called the Burkett profile, which looks like. So this you see at small r, this just goes to a constant, this just goes to rho naught, but at large r, it has the same 1 over r cubed scaling as the NFW profile. Like, note that like if you compare like the Burkett profile to an NFW profile, it's not always true that the Burkett profile will give a smaller signal for indirect detection. It depends what part of the halo you're looking at. So like this is not using Burkett always is not always like the most conservative choice when you're trying to get a small signal. But if you look at the galactic center, typically it will be the smallest by a friendly question.
Do these come from bits of the data, these profiles, or from something like simulations? I understood.
Good. So the NFW and INASTO primarily come from fits to simulations. So like the data, so right. So these functional forms come from looking at a bunch of halos and simulations and saying, okay, what's a simple numerical form that we can fit that describes the halos and the simulations reasonably well. I should say, I mean, these are definitely approximations, and like just as one example approximation, both of these are spherically symmetric. Real halos and simulations, especially once you get into the outskirts, are not spherically symmetric. But the central part of halos can be quite symmetric, and so if you're looking at the galactic center, that is probably not a terrible approximation. But yeah, so these profiles were originally based on let's look at large simulations and let's try to describe how halos behave. The parameters for a given halo, and when looking at like the Milky Way galaxy and trying to get the profile towards the center, we don't have a huge amount of data on what the dark matter distribution is towards the Milky Way center. There are some upper bounds from looking at the distribution of stars, but they allow for a pretty wide range of density profiles. So what people typically do in those analyses is that they try putting in like these fitted profiles and they say, okay, if we made the profile really extreme, would it disturb how stars were propagating in the galactic center? And the answer is yes. But my recollection is like a flat profile is fine, and so is an NFW, and so is a modified NFW profile with an inner slope as steep as like 1.5. So this is an inner slope of r to the -1, r to the -1.5 is probably still fine. So that means that, you know, within the observational constraints, there's a lot of possibilities. So for smaller halos like dwarf galaxies, again, typically what people will do is fit this kind of model to them, or get a more complicated non-parametric model to the orbits of the stars and use that to try to extract the parameters of the profile. There are large, so I said there are large uncertainties. So there are large uncertainties associated with the inner parts of large halos. Small r due to the effect of baryons. And because, so we have observational data on how things are moving in the inner galaxy, but most of the mass is baryons if you're at the center of the Milky Way. And so then it's pretty hard to unfold what the dark matter effect is. But in small galaxies like dwarf galaxies, there are fewer baryons, so that is potentially less of an effect, and we actually constrain the J factors observationally. But in dwarf galaxies with very few stars, there's just not a lot of data, and so the answer that you get can depend quite a lot on like what kind of model you use to model the dwarf galaxy in the first place.
From the center into it?
Yeah, from the center of the Milky Way. No, it's a good question. So the question was just when I write R here, do I mean from the center of the Milky Way? Yeah, so I mean the same R coordinate in these, which is not the same R coordinate as what I wrote down in the line of sight integral earlier. So let's let me let me go to that point in a moment. Okay, and be large uncertainties. So the caveat for dwarf galaxies is, make sure that the uncertainties on the J factors are properly taken into account, because dwarf galaxies with very few stars are great clean places to look for dark matter because there aren't many baryons. But if you don't have many baryons, that also means you don't have many traces of what the dark matter is doing. So, right. Okay. I also want to say that like these profiles are just the smooth profiles. So these are the smooth density profiles, but in realistic dark matter halos, there will be substructure, because as dark matter structure forms throughout the history of the universe, smaller halos get accreted into larger halos, and that's how halo assembly works. So that means that in any large halo, there will typically be smaller clumps of dark matter within the halo. These are smooth densities. Every halo has substructure. And that substructure can really enhance annihilation signals by quite a lot, because annihilation cares about the average of the density squared through the halo. This is not a thermal average now, this is a position average across the halo. So annihilation cares about the average of the density squared. This is what controls the signal, but this is larger than the average density of the halo squared, and can be a lot larger if there's a lot of small high density clumps within the halo. So unfortunately, these substructure contributions often come with quite large uncertainties, because as Annika mentioned yesterday, in these simulations, the dark matter particle could be, an atomic scale particle. The size of the particles in the simulations is maybe 100 solar masses. In models like in WIMP models, the smallest substructure scale could be down at like 10 to the minus 12 solar masses. So understand, and those very small halos could also be very dense and could give big contributions to annihilation, but it's hard to simulate that contribution in detail. So you will sometimes see people quoting boost factors, by which they do not mean a Lorentz boost factor, they mean the ratio of the annihilation that you would get, the total annihilation that you would get to the ratio that you would get just from the smooth halo. And these boost factors may be like several orders of magnitude. So if you see an analysis that's claiming like a very large boost factor, be aware again that number probably has substantial systematic consequences. Okay, so that all said, and uncertainty, and in particular, this is especially true for large halos for galaxy clusters, because they're very big to have a lot of substructure. Okay, so and just to give you, so all that said, if we just look at the smooth halo and we ignore substructure, and I ask what are sorts of the typical J factors that I would get associated with these profiles, the sort of typical size of the J factor with, so if we look at the galactic center region with a 1 degree radius around the GC, then you get, and let's assume an NFW profile. If you plug in the numbers, you'll get a J factor of about 10 to the 22 GeV squared centimeters minus 5. And whereas from dwarf galaxies, the individual J factors of dwarf galaxies are more in the range of, I expect to be more in the range of J of 10 to 17 to 20 GeV squared. Minus 5. I was going to do an example with these numbers, but then I realized that I asked you in one of the exercises to do basically the identical example. So I do suggest that you take a look at the exercise, try plugging the numbers in, and if anything is confusing or unclear, please just let me know. I did notice going through the exercises that there are places where I wasn't super clear, so I'll be trying to send out a clarification on some of these later. So all I really want you to take away from this is, at least if you've got an NFW profile, the galactic center is probably a couple of orders of magnitude brighter than anything else in the sky. So this can be a great place to look for pretty faint signals, but it does come with this big uncertainty associated with this choice. And the galactic center also tends to have pretty high backgrounds. So distinguishing signal from background can be hard if the signal is not in a background feature. Okay, and then I just want to give you one more tip, and then we will leave J factors behind and say a little bit about backgrounds before going on 2 slides, which is that pretty often you'll be dealing with a situation, which goes back to this question of what is R. So previously I wrote an expression like this. Go of R squared dr for the J factor, or for decay. So the R here is the line of sight distance from the Earth. So it's the distance from the Earth to the annihilation point. Okay. But something like the NFW profile is expressed in a distance from the center of the galaxy or the halo. Okay. So if you're dealing with a system like that, you just want to think about the trigonometry. So like, let's say the Earth is here, the center of the galaxy or the system you're looking at is over here. And we'll say there's a distance d between them, and the annihilation is happening somewhere out here. So you want to know then how to convert between this distance from the annihilation point to the center of the system. Let's call that S. So this is the argument of NFW, etc. profiles. And this distance is the distance R that's appearing in our J factor integral. Okay. So in this case, trigonometry is your friend. The cos rule comes to your aid. So if we say that this, we call this angle theta. So this is the angle between the center of the system and the annihilation and the point that your telescope is looking at on the sky, then the cos rule just tells us that the distance S that we need to feed into our NS or NFW profiles is just going to look like the square root of R squared plus T squared minus 2dr plus theta.
Wouldn't setting the problem up in this way lead to an additional factor of uncertainty calculating that theta?
So theta is usually the thing that you observe in your telescope. Like it's, I mean, this is telling you like, well, yeah, so assuming that you can see the center of the system in your telescope, then you can measure the angle that the photon is coming in at. But you're right, I mean, a telescope is not going to have perfect angular resolution. You're not going to know exactly where a photon is coming from. And so that's going to lead to uncertainties because you're not 100% sure which photons are coming from, which point in the system. So that, that those like instrumental effects that say, and similarly for energy resolution, usually you won't be able to measure the exact energy of a particle you get an energy with some uncertainty. So that's also why, when we were talking about spectral lines or, power laws with sharp cutoffs, those are never going to be perfectly sharp because your instrument will always have some finite energy resolution. You will always see some scatter. So yeah, that is indeed just another factor that has to be built in when you're figuring out what kind of spectrum do I expect to see in my telescope. It's a good question. And yeah, just to clarify for people on Zoom, the question was just, is there an uncertainty associated with measuring theta? Okay, so this is how you do the calculation. You just when you're writing rho as a function of position here, let's put an explicit thing here. This is actually just a function of the S parameter. So you can just feed S into these rho quantities. And evaluate that as a function of R for some fixed theta. Okay, and in particular, when we're looking at the galactic halo, we often use galactic coordinates, which are just spherical polar coordinates centered on the Earth. And I'm just going to mention this because you're going to see it in some of the plots that I show later. Yes. The galactic coordinates L and B, which are galactic longitude and latitude coordinates. So in this coordinate system, the equator is defined as the plane of the Milky Way. That's at latitude 0. And we define the galactic center at L equals 0. So if we view like the celestial, if we view the sky as a sphere with the Earth at the center, and then we say, all right, you know, here's the North Pole, here's the galactic plane and the equator surrounding the Earth. So then L is like the phi coordinate. You know, L tells us about angle around the sky, and B tells us, so if we have like a point up here, B tells us about the angle above the equator. And so if you're used to dealing with like theta and phi coordinates, where theta is the angle from the North Pole and phi is the angle that goes around in the circle, B is like pi over 2 minus theta. And if you're doing, so in these cases, it's often helpful to just realize, so okay, and now theta, by theta, I mean the angle from the pole, not the angle between the annihilation point and the center of the galaxy. So if, so now I'm going to, having written the relation to the usual spherical polar coordinate system, I am now going to cross that out and say, letting theta be as defined above, so that theta, there is a relationship between L and B and theta, which is just that cos theta is equal to cos L times cos B. So for the Milky Way halo, this just means that you can easily write S in terms of cos L and cos B if you've got some, and that allows you to predict the distribution of your signal on the sky as a function of L and B. This is a handy thing to do when looking at galactic signals. And you could do some more things for magnets. System. Okay. So then before we get into the slides, the last thing, we've already talked about backgrounds quite a bit, but I just want to do a little bit of summary of that. So there are some channels for indirect detection that are expected to be essentially background free. We just don't know of any astrophysical processes that should give rise to detectable levels of these signals. That list is pretty short. So gamma ray lines or sufficiently sharply peaked gamma ray spectrum can be in this category. Anti-deuterons can be in this category. There aren't a lot of ways to make them through conventional astrophysics routine, and heavier anti-nuclei. Note that this statement that lions don't have backgrounds is specific to, like, the gamma ray thing is important here. If we look at lower energy lines, like once we get down into the X-rays, the X-ray lines have backgrounds from like atomic and nuclear transitions. Yeah.
Excuse me. What about the lines coming from accelerated photons? Wouldn't those also show up as gamma ray lines?
So like by accelerated photons, you mean like an electron comes in, hits a photon. So that typically doesn't give a line spectrum because if you just think about the collision, there's a range of angles. So even if you know exactly the electron energy coming in, there's a range of scattering angles, and the scattering angle determines what the photon energy is coming out. So you get a spectrum rather than just a line.
Okay.
And similarly, and usually, of course, your electron spectrum is not a delta function either. So the electron spectrum has some width, and that also broadens the photon spectrum. So X-ray lines do have backgrounds from known atomic and nuclear processes. And we'll see this when we talk a bit about the 3.5 kV line. Okay, so that's, if you want to look for a smoking gun signal in a background free channel, those, as far as I know, are basically your options. Now, when we think about backgrounds for continuum photons and charged particles, at least at relatively low, at least at the kinds of energies, the sort of GeV to TeV energies that we've spent a lot of time talking about, there are a lot. Just because all the processes that we talked about of like high energy protons hitting the gas, making secondaries, high energy electrons interacting with the starlight, upscattering it to high energies, these all work for conventionally produced electrons and protons as well, not just electrons and protons from dark matter annihilation. So this gets contributions from protons hitting the gas. So there can be a large background associated with the gases in Milky Way because it's continually being illuminated by this once of cosmic rays. ICS, CR electrons interacting with the radiation field. There's usually subdominant, but there's also bremsstrahlung as the electrons scatter off the gas. They will radiate as well. And then at lower energies, you can have synchrotron radiation. Is typically in the radio to microwave band. Like the cosmic ray electrons in our galaxy produce synchrotron radiation in the radio to microwave. And just our galaxy has a lot of stars. Stars can be a source of a lot of electromagnetic emission of low energies. Our galaxy also has a temperature, so the thermal emission can be relevant at low energies. And while stars produce a lot of lower energy emission, they can also give you high energy emission from, for example, pulsars or supernovae. And from active galactic nuclei, Slatyer creating black holes in other galaxies. So this, I mean, we live in a galaxy. Anytime we look at an area where there might be high dark matter, we have to look through the galaxy to do it. So these backgrounds are generally an issue for every signal, except these background free channels I talked about. All of these backgrounds are going to be worse if you're looking straight in the plane of the galaxy, because that's where most of the stars are and most of the gas is. The dwarf satellite galaxies are relatively clean, but because they don't have a lot of baryons. But the problem there is you have to look through the galaxy to see them. So a lot of these searches would be much easier if we could just, get out of the galaxy. But that's a hard problem. So okay. So that's basically what I wanted to say. So then for the remainder of this lecture, I want to switch over to my slides now. So I'll just pause there and ask if anyone has questions about anything that I've written on the iPad before I switch over to slides and start showing you some real results.
Yeah, I'm not sure I understand why you say that.
Can you try to explain again why the substructure is irrelevant for the T factor?
Good. So why is substructure irrelevant for D factor? So it's good. So if I'm looking, so it depends. So it's certainly true that if I can actually, and this goes back to the question about angular resolution actually, if I can resolve a small dense clump with very high density, that density will certainly enhance the decay signal from, okay? Like, so if I can resolve like an individual clump of dark matter or an individual small halo of dark matter, then yeah, like that will absolutely boost up the decay signal. If I have like many such small clumps and I can see them as like individual points, then that can also give me an interesting decay signal. Like it would change the power spectrum of my decay signal. But if I'm in a situation where my angular resolution stuff is that I really just have to like average over the whole region of the galaxy cluster, then regions with higher density will have more decay and regions with lower density will have less decay. But at the end of the day, what I'm looking at is just the average density because decay only scales like 1 power of the density. So what I will probe in the end with my overall decay signal from that system will just probe the overall dark matter density in that system, not local variations in its density. Okay. Whereas for annihilation, even if I'm averaging over the whole system, the average of rho squared is not the same as the average of rho all squared. Does that make sense? So yeah, I mean, it makes a difference as to whether you can resolve structure within the system or not. If you can resolve the structure within the system, like dwarf galaxies is a substructure of the Milky Way. So, we can look at dwarf galaxies and get a constraint from the dwarf galaxies, which is different from our constraint from the whole halo, because we can see them as localized overdensities. But I mean, just as an example, gamma ray telescope. So like the Fermi Gamma Ray Space Telescope at energies above 10 GeV has an angular resolution of about 0.1 degree. The size of the moon or the sun on the sky is about like 0.5 degree. It's about 0.5 to 1 degree. So I don't remember the exact number, but it's in that ballpark. So like Fermi spreads point sources out to a scale that is not much smaller than the size of the moon or the sun. Like every star looks like the moon or the sun in Fermi. And so that means that for a distant galaxy, you're going to see a point.
I know the Earth's rotation around the sun is relevant to take that into consideration for direct detection sources. Is that also relevant for indirect detection?
That's a really interesting question. So the question was, do we need to worry about the rotation of the Earth around the sun? Good. So for most indirect detection searches, the answer is like no. Like you can work out, how. It's no, provided that you have reconstructed, you have made the conversion from the angle at which this photon hit my telescope to where in the sky did this photon come from, right? I mean, obviously, if your telescope is like swaying back and forth, looking around, then a photon that hits the detector at a 30-degree angle at one point in time may not be coming from the same place as the photon that hits the detector at a 30-degree angle from another point in time. So typically fortunately, as a theorist, the experimentalists usually do that conversion for you. And so like in a lot of public data sets, you'll have photon directions reported in terms of where do we think it came from on the sky, as opposed to at what angle it hit the detector. But once you've taken that into account, then in most cases for indirect detection, you don't need to worry about the orbit, just because the change in distance due to the orbit of the Earth is super tiny compared to the size of the sun, compared to like the region of which the integral has support. But as an exception, so I found this out a few years ago, when you're doing something that depends like on sensitive timing, so say you're looking for pulsars, then you do care quite a lot about the exact position of the Earth and like how the relative velocity of the Earth and your pulsar is changing over time, because you're relying on extremely precise timing, and you're relying on extremely precise timing, and so there the correction for where is the Earth and how is it moving actually becomes really important. And if you get it wrong, you won't find any pulsars. Pulsars are an important, and this makes it a lot harder to search. There was an idea for doing sort of like mass searches for populations of pulsars, even if you can't see the individual pulsars significantly. But it turns out that this is an issue, because to work out the necessary correction, you also need to know the location of the pulsar on the sky really well. So if you're doing a blind search, you just have to very finely grid the sky, and that gets computationally very expensive. So yeah, so there are cases where it matters, but for most cases, like if you're just asking how does the orbit of the Earth around the sun change this integral mostly has support over like 10 kiloparsecs. So the difference of the Earth's orbit is pretty small. There's a question after that. We're getting here as an exercise. Practice mountain climbing.
Sorry. Hi. In terms of the boost factor, is there a way to work these closely with simulation and perhaps integrate kind of more of the actual substructure within itself rather than just a general blanket term?
Yeah, so the way that people estimate boost factors is indeed by using simulations, but the problem is that the simulations typically only go down to like the scale of an individual particle in the simulation may be larger than the substructure that you think is dominating your annihilation signal. So it's just hard to resolve very small halos. So people have done like some very zoom-in simulations of very tiny halos to try to figure out how their concentration would scale. But the basic problem here is that often in structure formation models, the smallest halos are the ones that formed at the earliest times, which means that they formed when the universe was most dense. And so you can expect them to have pretty high densities and to be pretty like concentrated, to be pretty compact. And depending on the degree to which that is true, they may end up totally dominating the signal. And so then your signal is being totally dominated by small structures that you that are impossible to simulate in cosmological simulations. So this is why there are substantial uncertainties. There are also other types of uncertainties where the simulations may tell you, so cosmological simulations can tell you how the structures get formed, but not necessarily what their subsequent life is. So the question of in the inner parts of a galaxy or a galaxy cluster, as these subhalos pass through the baryonic disk, do they get disrupted? When that happens, that's again a question that you can try to answer with simulations, but people have over time got varying results. So yeah, but yeah, I mean, like there has been work in this direction to try to better simulate like super tiny halos, not starting from the cosmological box, but really zooming in and try to better understand how they work. And I think over the years that has tended to bring down the expected boost factors compared to what you would have gotten by like some of the earlier studies basically just said, okay, within the mass range that we can see, the concentration of the halos is scaling like a power law. Now let's extrapolate that power law down 17 orders of magnitude. That tends to get you quite large boost factors, and the more sophisticated analyses seem to have lowered them somewhat. But this is part, like you'll often see in constraints, people basically just setting the boost factor to 1 because it seems like sort of the most conservative thing to do. But I mean, it's true, like it's probably not 1 in a lot of systems, and a better understanding could maybe allow us to set stronger than us.
Brilliant, thank you very much.
No, it's a really good question. This is an open problem.
A bit following what Steve has asked, I heard that for resolving these small substructures, people typically use these analytical recipes like the surveillance mass function or based on the halo model, but I don't know if people typically trust these analytical calculations or not.
Yeah, I mean, so yes, people sometimes use analytic or semi-analytic prescriptions. People sometimes try to do simulations down to some scale and then build like some analytic or semi-analytic prescription based on that. My personal feeling is that these are very good for estimates, but it's hard to trust them to the level that you say, okay, if I have a model that is totally ruled out, if I have a boost factor of 100 and totally fine if I have a boost factor of 10, do I believe these enough to convince me that the boost factor is 100 and not 10? The answer for me is probably no. So, but I mean, this is just my personal opinion. So, but I mean, I think it's great that people are doing those estimates, but I don't think I'm not sure that we understand the system well enough to be able to give a number that we trust so completely that we can say, right, you can stop thinking about the dark matter models that are ruled out if you assume this boost factor is true.
And a second question. These backgrounds, are they taken into account in the codes that you mentioned the other day?
Like our prop and data for the cosmic ray propagation, yeah. So those codes will also give you an estimate of the conventional cosmic ray signals. Okay. But I mean, yeah, like, but yes, that's it. I mean, they'll take account of the backgrounds that we know are there. Like we know the galaxy is full of cosmic rays. But you can certainly have situations where there's a background that we didn't expect or that we don't know how to model that shows up in your data. And that's, many of the anomalies and excesses that I'm going to talk about later are probably in that category. Like it may not be telling us about dark matter physics, but it's also not just a statistical fluctuation. It's telling us about some genuine physics that is going on in our galaxy that we didn't know about before. Okay, I am going to stop sharing. So these are great questions. Thanks, everyone. I'm going to stop sharing on my iPad, the Zoom room with my iPad, and then I am going to attempt to share screen. Okay, so now I'm going to attempt to share screen with my laptop. Sorry, just okay, can everyone see that okay? Can we check that our Zoom is now? Okay, so for the remainder of this lecture, I want to talk about the status of current error detection sections. So where I'd like you to be, and this will, this will almost certainly partly spill into tomorrow's final lecture. So we'll see how far we can get today. So where I'd like you to be as we get through this section is to have an idea of what the general landscape is of upcoming telescopes and experiments relative to indirect detection. This is a huge amount of information, like all of these telescopes have white papers. I'm not going to try to summarize all the properties of all these telescopes, but at least hopefully you will have the names so that you can look them up for information. I want to discuss the strengths and weaknesses of different targets and different channels for indirect detection. And I want you to have an idea of where the leading indirect detection detection constraints currently are for both annihilation and decay across a range of dark matter masses and final states. Okay, so that's good. At this point, you should have, so yeah, like at this point, I think you should have all the concepts you need to understand all the signals in the slide. But of course, definitely ask me if anything is unclear. It's quite possible that I forgot something. Okay, so first, landscape of upcoming telescopes. All of these plots are taken from this nice review that Rebecca Lean wrote last year, which has just like a nice summary with references of a lot of the upcoming telescopes. So in X-rays, so axes here are the year in which the telescope was active, the year which it covers, and the energy of the energy which the telescope is sensitive to. So we are here over in 2020. I think this review was written in 2019 or 2020, so some of these are a little optimistic. Like MicroX has had its first flight, but hasn't done a dark matter search yet. But this is basically what we are. So in the present day, the landscape is that at relatively low energies at the KeV to MeV scale, there are a lot of competing X-rays. There are a lot of X-ray experiments. And so X-ray signals we can confirm in multiple detectors typically. So NuSTAR, Suzaku, Integral, Chandra, XMM Newton, and now like Zeta, which isn't on here. These are all currently active telescopes in the X-ray band. Then there is a bit of a gap. Like in particular, in the MEV to GeV band, there are not a ton of telescopes at the moment. There's Integral, which is a rather old instrument. It's been up since 2002, I think, although it can still say interesting things. And then at higher energies from like the tens of MeV band up to about the 10 to 100 GeV band, the Fermi Gamma Ray Space Telescope basically reigns supreme. It is the main way to look for especially particles in sort of the classic WIMP dark matter range at about the sort of 10 GeV to TeV scale. Fermi is a space-based telescope, which is why it has this unique sensitivity. As you go to even higher energies, there are ground-based telescopes, which are looking for the effect of the high energy photons hitting the atmosphere and making a shower of secondary particles, which the ground-based telescopes can look for. But that technique loses sensitivity below about 100 GeV, and you have to go to space. So below 100 GeV is basically Fermi all the way. At higher energies, we have a range of ground-based telescopes, such as HESS, Veritas, MAGIC. Hawk uses a slightly different detection technique, and LASO is one that's just started taking data in China.
So these high energy ground-based telescopes are basically reconstructing from showering?
For a minute, yeah. So the classic technique here in these Cherenkov telescopes is that you look at a shower of Cherenkov light and you try to reconstruct the energy and the angular resolution of the telescope. They actually have pretty good angular resolution. The angular resolution is like 0.1 degree, so similar to Fermi. The energy resolution is not as good usually. It's more like 10 or 20% in the current telescopes. The CTA, which is the upcoming telescope in this band, is I think meant to have significantly better energy resolution. So, and also just like much better sensitivity. So the CTA is actively being built, but it's sort of the next generation telescope in that band.
So I guess these ground-based shower reconstructions, they wouldn't really know if it came from a gamma ray or a cosmic ray. Is that right?
That's their major background, trying to tell the gamma rays apart from the cosmic rays. You can discriminate based on the shower shape, but they do for a lot of their analyses, they'll do like an on-off analysis where they look at the region of the sky they're trying to look at, and then they look at a neighboring region of the sky where they expect the backgrounds to be similar, and then they subtract the two from each other. This can sometimes mean that, I mean, the other way to do it is just trying to model the cosmic ray backgrounds in detail and then subtract them. But yeah, this is their major background, that they can't necessarily tell if a high energy particle coming in is a cosmic ray or a gamma ray.
So I'm sure they can put that and also just study cosmic rays if they want.
Yes, they can also do cosmic ray studies. And this is, there's actually an interesting aspect of this. It turns out that, so I talked earlier about anisotropy in cosmic rays and using that as a probe of the sources of the cosmic rays, and said that even if it's just one relatively nearby source, it gets suppressed to down to the percent level. But there was a paper a few years suggesting that these Cherenkov telescopes would actually be the best way to look at anisotropy in cosmic rays, because they see a lot of so because they're ground-based, they can have pretty large collecting areas. So just to give you a baseline, the Fermi telescope has a collecting area of about a square meter, or a tenth of a square meter. The ground-based telescopes can have collecting areas of like 10 to the 4 to 10 to the 5 square meters. So once you're above their energy threshold, the other issue is Fermi is an all-sky telescope. It looks at a third of the sky at a time. So like every 3 hours it sees the whole sky. So but Fermi has 10 years of archival data at this point, which is basically over the whole sky. The telescopes that use the Lecture4 technique can only look at a relatively small region of the sky at a time. So they're pointing telescopes. But once they point and stare at an object for long enough, they tend to get the strongest constraints. Was a question? Yeah.
Okay, could you explain like what fixes the energy range of these telescopes?
Yeah, so as I said, so the reason that the high energy gamma ray telescopes don't extend to lower energies is because they have this threshold that like lower energy gamma rays don't make an observable and reconstructible channel, as I understand it. I do not know the details of how you calculate that energy threshold, so I'd point you to the literature for that. For Fermi, the issue is that at lower energy, so then Fermi's upper bound, Fermi can see higher energy gamma rays. The problem is that with only a 1 square meter collecting area above about the TeV scale, the number of gamma ray photons starts to become very small. So it is just a statistics issue. At the low energy end for Fermi, the problem is that the way that Fermi works is when a gamma ray comes into the detector, it Keck reduces. And so it makes an electron and positron, and then Fermi has like silicon tracking layers, and you track the charged particles through those layers, and then you trace them back to the origin point and reconstruct where the photon came in from. As you go to lower and lower energy particles, they tend to scatter multiple times in the detector, which makes it hard to reconstruct where they came from, and Fermi's angular resolution just gets really bad at low energies. And eventually, they won't have enough energy to Keck reduce, and this technique stops working altogether. So then you have to think about like Compton scattering instead of Keck reduction as the interaction process in the detector. So that's what says like Fermi's lower band. I know less about the X-ray telescopes yeah, I mean, in most cases, you can make certain design choices to try to optimize energy resolution or angular resolution or sensitivity within some range. And it's more efficient to have a bunch of telescopes that are optimized for somewhat different energy ranges and resolutions than to try to do everything in one telescope.
Right, thank you.
Okay, so yeah, if you're interested in upcoming experiments in so I'll say a little bit more in the future about these proposed future experiments in the MEV to GeV band, like Astrogam and Amigo. The X-ray band, there are a bunch of upcoming experiments that will improve current ones across a range of these metrics like energy resolution, angular resolution, sensitivity. But again, each of these experiments has like tens of pages, white papers describing everything that they do. So I'm just going to basically refer you to the literature, but with these names, you should at least be able to find the white papers. So that's at the high energy photon end. At lower energies, we have a range. So then another band that is often interesting, looking for synchrotron signals or looking for this cosmic microwave background or 21 centimeter signals from the early universe, are the radio and microwave telescopes. And these can also be very important for finding pulsars, which you will see show up as a common source of annoying backgrounds in the searches that we're about to look at. So Planck has given us our best measurements of the bulk of the CMB, but that mission is over now. There are future planned CMB experiments like the Simons Observatory. At lower energies, there's this range of telescopes that are, and this is a subset, there's a longer list. I can give you the longer list if you're interested. But these telescopes are precursors to a big planned experiment called SKA, which will sort of is planned to be like the big flagship radio observatory of the next generation. So this will be both a 21 centimeter search experiment and like an excellent pulsar detector. So EDGES is the experiment that has claimed the first detection of primordial 21 centimeter radiation, but there's a large number of other experiments not shown on this plot, which are also trying to find primordial 21 centimeter radiation. The list is in the notes, but also ask me if you want it. Meerkat is distinguishable as one that will be particularly good for finding pulsars around the inner galaxy. Okay, so that is, the sort of broad approximate picture of the telescopes you think about when you're looking for photons. Which, and I'm missing some energy bands like the optical band, we have the Hubble telescope, we have various surveys looking for the distribution of stars. These could also be important probes of dark matter. They tend to be less relevant for indirect detection searches for the models that people usually think about. In cosmic rays, there are really sort of two distinct bands. There are experiments searching for extremely high energy cosmic rays, such as the telescope array and ANITA. So this is up at the 10 PeV and higher band. And there are the telescopes that are more relevant, and these are often looking for extragalactic cosmic rays. So these are very rare, very high energy events. And then at lower energies, we have a whole ensemble of experiments looking for cosmic rays in sort of the GeV to TeV range. AMSO2 is the current sort of flagship experiment at lower energies. There are also experiments like DAMPI and CALET that are looking in the same energy range. The thing that is special about AMSO2 that is it has a magnet, which a number of the other experiments don't have, which means it can distinguish charge. So it can tell matter from antimatter. So AMSO2 typically sets the most sensitive limits for classic WIMP dark matter at the moment. But at higher energies, telescopes like Quark, which is also a gamma ray telescope, a ground-based gamma ray telescope, can set important limits. CREAM is another experiment measuring cosmic rays at these higher energies. I will also mention, not on this plot is the Voyager telescope, which would be like way back off the top of this plot. But as I mentioned earlier, it's actually very sensitive to lower energy electrons and positrons. That's a question.
I see your bullet point down here about the super high energy cosmic rays setting limits on the ultra heavy decaying dark matter. Are there other potential sources that we know of these super high energy?
Of really high energy cosmic rays? So like people think about, BSM physics that might not necessarily be related to dark matter. But I'm not an expert on this. I have a reference later on to like a white paper about searching for some various ultra heavy novel particles. But I don't have a good sense of what physics is proved by those ultra heavy things. If someone in the room does, they should feel free to speak up. But I can point you to, I can point you to some.
But almost definitely it will come from the decay of some very heavy particle.
I don't think we know of a way to get particles. So we're talking about like the sort of way above the EEV scale. I'm not sure we know of conventional accelerators that can get things that high. So that said, you may say, I'm not sure, as opposed to I know for sure we cannot get it that high with conventional physics. I don't have a high level of confidence in that statement, but the examples that I've seen of the searches we would do are all in the context of there's some new heavy exotic state.
Any comments on the gap?
On the gap,
About the PV?
on like the PV or 10 TV, I probably can't say anything super enlightening about that gap. I guess it's basically the difference between are people focusing on looking on understanding cosmic ray propagation in our galaxy, or are they looking for extragalactic cosmic rays? And these things and these like two goals suggest different approaches, and the first group is mostly the former and the second group is mostly the latter. But I don't have a good sense if there's some like exclusion, if there's something that makes it really hard to build a detector to see in this gap. I guess IceCube covers this gap with the neutrino searches. So if you have something that's making very high energy cosmic rays, it will probably also be making very high energy neutrinos, and IceCube has sensitivity across this gap. But I also, I don't know how sharp these thresholds are. Like this is Rebecca Lean's sketch of where the thresholds are. But I think it is true that there are broadly these two groups looking for somewhat different physics. Again, people who know more should feel free to speak up. Okay, so then neutrino telescopes, again, we coming to that point. So at the moment at the high energies, Antares and IceCube are large neutrino experiments. Antares has instrumented a large volume of water in the Mediterranean. IceCube has instrumented a large volume of ice down at the South Pole. So these are both enormous neutrino detectors, and they currently typically lead the limits for decay or annihilation to neutrinos. At lower energies, we have experiments like Super Kamiokande. And coming up, we have Hyper Kamiokande in June. And these can have sensitivity, as was discussed earlier. These telescopes can have sensitivity to dark matter capturing the sun and then annihilating and producing neutrinos. And there are also models of dark matter where the dark matter decays in mixed relativistic particles, which then have signatures similar to neutrinos and could be detected in neutrino detectors. But these lower energy experiments are typically not the most sensitive ways to probe light at DM. Neutrinos are hard to see. In particular, these experiments tend to become competitive with gamma ray searches for annihilation just to hadronic channels, which, as we said, make neutrinos along with everything else. If you go to sufficiently heavy dark matter, because neutrinos interact better as you go to higher energies, and up at the like PeV and 10 PeV scale, these can sometimes have the strongest bands.
With the searches for dark matter capture in the sun and then production of neutrinos, is there something that would distinguish those neutrinos from the solar neutrinos that we usually see?
I assume that, so they could potentially be much higher energy. Like the energy spectrum would be very different. I think that's the way you would distinguish them. Gotcha. Yeah, question mark?
Wait.
Okay, just maybe a naive question, but is the energy scale here, is it directly proportional to the dark matter energy, or is it?
No, excellent question, good. So this energy scale is the energy of the particles that you detect. So in a lot of circumstances, that will be closely related to the dark matter mass. So like because the dark matter is non-relativistic in our galaxy. So when two dark matter particles annihilate with each other, the total amount energy you have available is twice the dark matter mass. When the dark matter particle decays, the total amount of energy you have is the mass of the dark matter particle. So if you just annihilate like pretty promptly into particles which then never interact again, such as like DMDM goes straight to neutrino, anti-neutrino, then the energy will just be the dark matter mass or close to it. But if you go through intermediate steps, either through a cascade on the standard model side, or through you make a high energy. You make a high energy particle and then it scatters and makes a bunch of secondaries, then the particles that you see may be very different to the mass scale of the dark matter. So I'll give you an example of this a few more slides further on, which is showing the constraints on heavy dark matter decaying into like big quarks. And so at the like PeV to 10 PeV scale, the strongest limits on that come from IceCube. Where the situation is when these things hadronize, they make neutral pions, they make neutrinos, and just like look for the neutrinos. So that's a pretty short cascade, and the neutrinos don't really interact after being produced. But at lower energies, at somewhat lower energies, the strongest constraints come from Fermi, even though this is an energy way higher than Fermi's than the range that I showed for Fermi on this plot. And the reason is because you're producing particles which undergo a long particle cascade and which spit out a bunch of 100 GeV to TeV photons, and Fermi is great at seeing those. So yeah, this is detection. So there's a possible connection to dark matter mass, but they can be decoupled by the production of secondary particles and by cascades. It's a really good question. Okay, so that's basically, I think that is close to the complete list of telescopes that are usually looked at for decay and annihilation constraints. It's not going to be a fully complete list, as I mentioned, especially in like the microwave band. There are definitely telescopes missing from this. And you can also do sort of more exotic, in particular, there's been a fair bit of work recently on looking at compact objects. So like looking at neutron stars, looking at supernovae, using that. Tanya talked a little bit about some of these bounds, using that to place constraints on dark matter properties. So in that case, it's, whatever energies the object emits in, you should probably try to look at it in those energies, and that may make a different range of telescopes interesting. But for just annihilation or decay out in space, this is, I think, broadly speaking, the range of current and upcoming telescopes that are interesting. So let's look at what they see. So we've already discussed a little bit the range of possible indirect searches. There are lots of options. We can look at the dwarf galaxies of the Milky Way, we can look at the galactic center, we can look at the halo of the galaxy that we're immersed in, we can look at extragalactic objects, other galaxies and clusters. We can try to look for clumps of dark matter that don't have baryons associated with them, either in a blind search or for some of the larger subhalos, we may know where they are. And we can just look at sort of the average background radiation over the lifetime of the universe. The advantage of dwarf galaxies is they're relatively close and they don't have a lot of background. The advantage of the galactic center is that we expect it to have a really high J factor, and it's close, but the disadvantage is that the backgrounds can be scary. The galactic halo, well, we're inside the galactic halo, it's as close as we can possibly be. If you're looking over the whole sky, also gives you sort of the maximum amount of information, the maximum amount of area. But again, the backgrounds can be complicated because the Milky Way galaxy is a complicated system. We can look at other galaxies and clusters. They potentially have a large dark matter content. This comes back to this question of boost factor. There are models in which the boost factor is pretty large, and that could significantly enhance the average signals from extragalactic objects. They can potentially give us information about the redshift the signals are coming from. We discussed this a little bit earlier. You know, if we know, so for example, suppose you'll see an example of this later. If we look at multiple clusters at different redshifts and we see a lion signal coming from different clusters, then we have an automatic consistency check. Are the energies of the lions consistent after we apply the redshift correction? So that can be powerful, but they're sensitive to the amount of substructure. The dark matter subhalos, I mean, this would be great if we could find these objects. They would probe the small scale structure. They can tell us about the properties of dark matter, and they could have relatively low baryonic backgrounds. The problem is that with no baryons as traces, it's hard to tell what they are. And for the extragalactic background radiation, this holds information about halos at all scales and over the whole edge of the universe. Again, it can be quite sensitive to what we think the halos on small scales are doing. So people have done searches of all these types from all these areas. There's enormous literature in indirect detection. I will now show you some samples. Okay, so I first, yeah, we're definitely not going to get through all this lecture, but that's fine. We have another one tomorrow. Okay, so where I want to begin first is by thinking about the return to the cosmological limits that we discussed in day one, which is a topic near and dear to my heart as I've spent a fair bit of time working on this. So we can work out the detailed version of those limits, and just as for other signals, our mechanism here is we need to know from your dark matter model, what is the spectrum of stable standard model particles produced by annihilation or decay, and then how that injected spectrum translates into an observable. This will be the example I mentioned of another case where propagation of the particles is important. So the first part we can do with Pythia or HERWIG or PPPC for DMID, just as we did for other indirect searches. The second part, we need to model how high energy particles cool and lose their energy in the early universe. So we're going to make some, so this is a prelude, we're going to make some simplifying approximations here. We're going to focus just on electrons, positrons, and photons. So the reason why we're not thinking about neutrinos and protons and antiprotons and heavier nuclei and antinuclei is because the neutrinos don't really interact at the epochs that the CMB is emitted and after. They're being decoupled from the standard model, from the rest of the standard model for a fair time then. And for protons and antiprotons, we could include their contribution, but they tend, any hadronic final state tends to make a lot more pions than it does protons and antiprotons. The branching ratio to those and heavier nuclei tends to be pretty small, and they're not super efficient at depositing their energy. That's what the studies have indicated. So we usually just zero out that contribution, but you could do the calculation of that contribution. It might make the constraints a little bit stronger. The other approximation we're going to make is that we're injecting a small enough number of particles that it's very rare they will interact with each other. So we're only going to take into account interactions between the ejected particles in the background, not between injected particles and ejected particles. And that means that the problem is linear in that sense. If I double the number of injected particles, I'll get twice as many interactions between the ejected particles in the background. Okay, so what those two assumptions do is basically reduce the problem to saying, okay, if I throw an individual high energy electron or positron or photon into the universe at some energy and some redshift, what happens to it? Now, I notice like from this point, the problem is all standard model physics. All the dark matter particle physics went into how do I get these electrons and positrons and photons in the first place? From this point, it's just atomic physics in the early universe. So the cascade that we're modeling here is shown schematically on this slide, and I guess I can use a stick now. Okay, so here I've tried to indicate by green are the background particles. Red and blue indicate particles that are carrying the energy of the injected particle. Okay, blue means electrons and positrons, and red means photons. So if I inject a high energy photon into the early universe, I can ask what happens. If it's high energy enough, what happens is it very quickly produces against the CMB. It produces an electron and positron, so then we go over to the left-hand side of this cascade and ask, okay, what happens to a high energy electron in the early universe? The answer is that it very quickly inverse Compton scatters on the CMB if the electron energy is moderately high. So that makes more high energy photons, which you then need to feed back into the rest of this cascade. As the photons get to lower energies, other processes become important. Photons can just scatter on CMB photons and lose energy. They can pair produce against the gas rather than the CMB. At lower energies, they can Compton scatter, so they can just bounce off the ambient electrons. And at sufficiently low energies, they become very efficient photoionizers. On the other side of the plot, down to relatively low energies, when they're non-relativistic, electrons' main energy loss mechanism is just inverse Compton scattering. Positrons behave the same at high energies. At low energies, the positrons can annihilate away, making more photons. Back to the other side of the cascade. The electrons at sufficiently low energies will excite and ionize and heat the hydrogen and helium gas and the bulk of ambient electrons. So I and my collaborators and also some independent groups have written codes which model this cascade. One subtlety is that for the electrons, all of these cooling processes are fast relative to the Hubble time. And so you can largely, if you were only looking at the electrons, you could ignore the expansion of the universe. But for the photons, this isn't true. A bunch of these processes have timescales around recombination and shortly after that are very comparable to the Hubble time. And so at the same time that you're working out this cascade, you have to take into account that the universe is expanding as the cascade is proceeding. But essentially, the code for this, like it's just a time stepping code. You start early in the universe, you inject particles, you look at how this spectrum evolves. Okay. So that gets you from an injected photon at some redshift to a distribution over redshift of excitation and ionization and heating of the gas, and also production of low energy photons that are just going to free stream to the present day because they're too low energy to excite or ionize anything. Question?
This is kind of basic question, I think, but are we looking at annihilation and decay that happened pre-freeze out, or is that's happening currently?
Good question. So yeah, the question was, when do the annihilations and decays happen that give rise to these electrons and photons? So here, what I'm showing you is a calculus. So this is going back to the cosmological constraint. So I guess I wasn't super clear. I talked about the cosmological constraints in the first lecture. You could do this kind of calculation so the observables we talked about were Big Bang nucleosynthesis and the CMB and then heating at late times. So you can do this kind of cascade calculation for Big Bang nucleosynthesis. In that case, the universe is 100% ionized, which removes some of these processes. You're not going to ionize or excite hydrogen if they're all 100% ionized. That analysis has been done for BBN, and you get some bounce from that. The work that I did on this was focused on the CMB and heating constraints. So there you're looking typically at particles that have been injected at redshift of, a few hundred to 1,000. So this is long after freeze out, but also well before the present day. Question there?
You mentioned that the polarization happens for significantly like low energy photons. I would have guessed that the ionization process is more efficient with photons of high energy. Is it just like relative to
No, the photoionization cross-section scales strongly with energy, and until you get down to until it turns over at the threshold. But like KeV, but like 100 eV photons are better ionizers than KeV photons. It's just the cross-section has a strong energy scaling. Like it's true that if a high energy photon ionizes something, the electron that gets kicked off will have a ton of energy. But just the rate is much higher for lower energy photons. Yeah, it's a good question. Yeah, I have a paper from 2009 which has an appendix which has the rate expressions for all of these processes, but that's how it turns out. So having done that modeling, this tells us the power going into ionization, excitation, heating, and distortions to the CMB energy spectrum sourced by a high energy particle. So then the results of doing this calculation are tabulated in the accompanying material to this paper that I wrote back in 2015. So you do not need to do this cascade calculation yourself. You can just look it up. Now that assumes a particular background ionization history. The dark history package that my collaborators and I wrote a couple of years ago allows you to vary the ionization history that you're assuming and account for what we call back reaction effects, which basically just means that if earlier injections of particles change the ionization state of the universe, that can change how this cascade proceeds. So if you solve simultaneously for the evolution of the ionization fraction and the evolution of this cascade, then you can take those effects into account. Okay, so once you've gotten to the point of, right, I know how a high energy electron makes ionization or heating at a later time, how do you get that to an actual observable? I mean, I can't go back to the early universe with the thermometer. So what you need to do is feed these inputs. So there are differential equations that govern the evolution of the ionization and temperature in the early universe. And these are encoded in public recombination codes like RecFast or HiRec or CosmoRec or Dark History. And Dark History has an adaptation of RecFast in it. And so basically these extra ionization and heating provides extra driving terms in these differential equations. So the next step is take a public code, modify it. This has already been done for you if you're familiar with it. So the class code has this nice module called exoclass, which is modified to account for exotic energy injections of exactly this type. So you can just feed it the table of how much power is coming in to heating and ionization from exotic energy injections from the kind of calculation that I just described, and it will work out for you how the ionization and temperature history of the universe changes. Okay. So then once you've got the temperature history, you can compare that directly to attempts to measure the temperature of the gas using Lyman alpha or using 21 centimeter radiation. This upper plot here is from the Dark History paper and is just showing the predicted matter temperature of the gas as a function of redshift under different models. Some of these are just, what if you only had dark matter annihilation and you didn't have any stars turning on, and that was the only source of heating in the universe? Others of these also include a model for you have stars turning on and producing heating at late times simultaneously with the effects from dark matter annihilation and decay. For the CMB, you need to go a little bit further because ionization history at early times is not the direct observable. Ionization history at redshift 600 is not the direct observable. The cosmic microwave background radiation is. So as the CMB photons travel to us in the present day, if there's extra ionization, the CMB photons will scatter off the electrons, and that will modify their spectrum. So this plot on the right is, so again, using codes like HAM or class with exoclass, you can forecast how changes to the ionization history should affect the spectrum, the anisotropy spectrum in the cosmic microwave background. This is an example of what that looks like. So this is a perturbation to the CLs of the cosmic microwave background, corresponding to energy being dumped into ionization at different epochs in the universe's history. So like the yellow line corresponds to redshift 600, the green line corresponds to redshift 750, the red line corresponds to redshift 250. This spans the range from redshifts of like 85 up to 1200. Okay. So you may have already noticed something from this, which is that these perturbations are actually pretty similar across different redshifts, but they're not identical. So it is actually possible to tell the difference between energy injections occurring at different times in the universe's history.
Can you give us any intuition for why the sort of middle range redshift is dipping down farthest on this plot?
Yeah, so right, good, excellent question. So the question was, can you give us an understanding of why the sort of redshifts of a few hundred seem to give you the biggest signal in this plot? So these signals are normalized like a dark matter annihilation signal would be. So like the signals that I'm injecting at higher redshifts are actually larger than the signals I'm injecting at lower redshift, because the dark matter annihilation rate scales like the density squared of the universe. Okay, so I'm injecting more power, like as we said earlier on the first day. Fan is higher at higher redshifts, so there's more power per baryon going in at higher redshifts, and these different signatures are normalized like that. So the reason why there's the reason why there's not a lot of signal for low redshifts, like the pink region here, is just because the universe is expanding, the dark matter is becoming less dense, the annihilation rate is going down. So I'm just injecting less power at that time. So this is not constant power per baryon. This is like power corresponding to a constant dark matter annihilation cross section. So that's why so that's part of the reason. The other reason is that the signal tends to get lower at low redshifts is because the universe also becomes more transparent as it expands. So it's less likely that your power makes it all the way down from the ejected high energy particle into ionization. But the main effect, I think, is just that less power is being injected in the first place. At high redshift, so the reason why, so this purple and blue lines are for redshifts of like 1100 and 1300, the reason is that at those times the universe is already fully ionized. So you can inject a lot of energy and it's not meaningfully going to change the ionization level because it's already over 99%. So in that case, you can inject a lot of energy and it doesn't change the CMB. So the peak of the effect of injecting power into ionization on the CMB is going to occur around redshift 600. Just because of these two countervailing effects. For decay, it turns out the peak is more like between like redshifts 100 and 300 because there's less of a boost effect from being early in the universe with high dark matter density. So, yeah, like, I mean, the details, so these two effects balance off, but the details of where the lines intersect is, is something you just have to look at. Okay, so having done this calculation for totally arbitrary photons or electrons and positrons, that are injected into the universe at early times, we can take linear combinations of these results to figure out the impact for a particular dark matter model that produces some spectrum of electrons, positrons, and photons. When we do this, you actually find that to the degree that there were differences between the different redshifts here, if I take linear combinations of injection at different redshifts and ask what does this look like for different dark matter models, well, all dark matter annihilation models have basically the same redshift dependence, which is density squared, and all dark matter decay models have basically the same redshift dependence, which scales with density. What you find that they have slightly different redshift dependences because particles injected at different energies take longer to deposit, can take a longer or shorter time to deposit their energy, but it's a pretty small difference compared to the overall density squared or density scaling. Okay, so that's the intuition, but what you find out empirically if you do this is that the imprints in the CMB of different dark matter models are for this reason basically identical up to an overall rescaling factor. So the only thing that changes about your dark matter model is how big is this characteristic imprint of dark matter annihilation or decay in the CMB. The annihilation and decay imprints are meaningfully different because they have different redshift scaling. But different models of annihilating dark matter are extremely similar to each other in terms of their CMB signal. And you can make this formula with what's called a principal component analysis. Yeah.
Yash, do you want to just unmute yourself and ask the question?
Yeah. So, I mean, sorry, just about the plot again and the things that we're talking about here again. I mean, so are these amplitudes, I mean, is this because of sensitivity of Planck to these CMB anisotropies at around redshift 600 or something? I mean, is this
So this is a perturbation to the observed CMB anisotropies in the TT channel, so the temperature correlations. Where this perturbation comes from is from a modification of the ionization history. Right, so what's actually being fed in here is you assume that some energy is deposited at the redshift marked here, by which I mean that we put in like a driving term in the evolution equations for the ionization and the temperature, which is like a delta function or close to a delta function at the redshift state of heat. So this is, I dump a bunch of extra ionization or heating into the universe at this epoch, and I ask how it changes the CMB. But the mechanism for that change is that that extra power raises the ionization level at all subsequent times. Those extra free electrons scatter the photons in the CMB. That modifies the pattern of anisotropies.
See, yeah, I mean, sorry. So I mean, isn't it also the case like the Planck satellite? It's also like for these dark matter annihilations. So the CMB anisotropies. I mean, it's most sensitive to around this redshift that for which we have.
This is the same signal. I mean that when we say Planck is most sensitive to dark matter annihilation around redshift 600, it is like that is this plot. I mean, like Planck is exactly observing this perturbation to the temperature anisotropies of the CMB. It's a signal that comes through ionization. Like, I mean, if you've seen Planck constraining dark matter annihilation, this is the mechanism. It's not, so you might think when you saw this the first time that maybe it was dark matter annihilation makes extra photons and those photons change like the black body spectrum of the CMB. There is a signal from that, but it's 5 orders of magnitude too small to see at the moment. So that is not where the constraint is coming from. The constraint is coming from modifications to the ionization history. Does that Does that clarify things?
Yes.
Okay, good. Yeah, so this is, when Planck says we set constraints on dark matter annihilation or decay, this is the mechanism through which they're doing it. So yeah, so let's go look at those constraints. So because all dark matter models lead to basically the same kind, all annihilating dark matter models or all decaying dark matter models lead to these distinctive imprints in the CMB anisotropy spectrum, we can characterize each dark matter model basically just by what the coefficient of that perturbation is. So they all perturb the CMB in the same way. What's different between models is how much they perturb the CMB. So we can characterize each model essentially by one number in terms of the CMB signal. And then the experimentalists can go look for a perturbation to the CMB that has that characteristic shape, constrain its coefficient experimentally, and you can compare that to the model prediction. So the way that we typically describe it, so if you think about what's changing the signal in the CMB, the way that we typically describe this is say, okay, the signal is going to depend on the cross-section for annihilation or the lifetime for decay. It's going to depend on the mass of the dark matter in the case of annihilation. And the other factors, we call this efficiency factor F effective as a function of E. So, and you can just, by modeling the cascade and looking at the imprint of the CMB, just work out what this effective efficiency factor is. So these plots here are showing calculations that I did a few years ago for annihilations to electrons and positrons or annihilation to photons. And this is essentially just showing as a function of the energy of the energy of the photon and the electron changes how fast it cools down and how much of its energy goes into ionization versus heating or excitation or other channels. That can be expressed in terms of an effective efficiency for changing the CMB. This is what these effective efficiency numbers are as a function of the energy of the particles. And again, we can just take linear combinations once we have a specific dark matter model in mind. So, and you can do the same thing for decaying dark matter, and these are results for decays from a paper that my student Chilean woman I wrote in 2016. So Planck sets an upper limit for annihilation on the combination of this efficiency factor, the cross-section, and the dark matter mass, that this result should be below about 3.2 times 10 to the minus 28 centimeters cubed per second per GeV. So as we argued on the first day, the constraint on the cross-section is going to get stronger for lower masses, because lower mass dark matter freezes out later for a thermal relic for a fixed cross-section. So if we then, and you can set a similar constraint on the lifetime, which is parametrically around 10 to the 25 seconds for decays. So when you ask what that translates to in terms of limits on the cross-section, so this is the limit from Planck, I think our colleague on Zoom was asking about earlier. So this is now a limit on the cross-section as a function of the dark matter mass, taking into account for annihilation to different standard model final states. So the strongest constraints so everything above these lines is ruled out. So the strongest limits are for the red and pink lines, which correspond to annihilation directly to electrons or directly to photons. These other colored lines correspond to all the other standard model final states except straight to neutrinos. They all kind of pile up because most of the other standard model final states put a significant fraction of their energy into neutrinos, but still have some appreciable branching ratio to electrons and positrons and photons. And that affects their efficiency because the efficiency of neutrinos is basically zero. So what we see, so I said on the first day to you that these CMB constraints end up ruling out dark matter, S-wave annihilating dark matter to intervisible states for masses below about 10 GeV. And that's what you can see here. So this dashed line is the thermorelic cross-section. So you can see that most of these lines cross the thermorelic cross-section line around a mass of about 10 GeV. And these limits continue basically linearly all the way down to masses at the keV scale. Although as you go to lighter and lighter masses, the range of final states that you can have becomes smaller because, you know, sub-MeV dark matter isn't going to annihilate protons. So this is the CMB bound, and these are for light dark matter down below the GeV scale. These are often the strongest bounds, at least on annihilation. The reason I'm showing it to you first is because these bounds are pretty model independent. They apply to almost all the final states except neutrinos. And so they provide like a good backstop for a lot of the other limits. If we have an energy range where we don't have a telescope that does a good job, the CMB constraints are always there. Yeah, I'm gonna I'm going to stop here for today, and then we'll continue with the constraints and the anomalies tomorrow. You can do the same thing for decaying dark matter. This is the comparable plot for decaying dark matter. So in this case, it's lifetimes below this scale are ruled out as a function of the dark matter mass. And again, this line stays more or less flat down to the keV scale. And you can see that we're typically constraining lifetimes between about 10 to the 24 and 10 to the 25 seconds, which is pretty much in agreement with our estimates from Monday. There are also, we can also, as I said earlier, take, we have a temperature forecast that goes along with this. So you can compare those temperature bounds to limits from Lyman alpha. I'll show you the actual plot for that tomorrow, but they're comparable to the CMB bounds for decay and weaker for annihilation, which is again, exactly what we expected from our parametric estimates on the first day. Okay, so that is my example of particle propagation is important for our early universe constraints. It's our first example of, an in-depth indirect detection constraint. So I'm going to stop there, take any more questions. But when we return tomorrow, you can see the next slide. I'm going to start going through I'm going to again sort of go back through the techniques that we've discussed over the last few days. So we'll start talking about cosmic ray and gamma ray constraints on annihilating and decaying dark matter. We'll go through all those. And then in the second half of tomorrow's lecture, we'll have some fun and I'll tell you about anomalies and things that we currently do not understand in the data. And I guess we have a discussion session this evening, so I'm happy to chat about any of this stuff. Thanks very much.